So it's the last talk of the day, but it will not be a very complicated talk. I will describe ongoing work that I have been doing with Eric Goubot about actually connecting the type of areas of fault-tolerant distributed task computability that Maurice introduced a little bit with epistemic logic. And so I will, in the introduction, I will have to describe the two sides of this connection. I will describe a little bit the specific distributed computing model that we are using and the goal in terms of task solvability. And then I will describe a little bit of background on the other side, on the logic side of epistemic logic and dynamic epistemic logic. And then really the talk will be a little bit what we have been mostly doing, which is actually getting right all the setting to be able to give a formal semantics to distributed computability in terms of logic. And a little bit, I will describe a little bit in more detail how we do that and some simple applications just to give you the flavor. And then for this conference, I think it will be interesting the last part of how, by going to the dual of the usual models used in epistemic logic, then you expose the topology information that is actually the reason why you can or you cannot solve a task in certain models. So, I mean, the goal of this project that we have been working for a few months and is to study fault-tolerant distributed computability of tasks from an epistemic logic perspective, specifically by using dynamic epistemic logic, which, as you will see, it turns out to be very, very natural, almost as if dynamic epistemic logic was designed to talk about task solvability in distributed computing systems. And then we get benefits from one area to the other and back. Hopefully, it's useful to reason about knowledge in distributed computability and in general to give a formal, precise semantics to what we do in distributed computability, which is usually just combinatorial descriptions, and it's not so clear what exactly is the semantics of the things that we have been doing. And in general, reasoning about knowledge is something that for many years it's known to be useful in distributed computing. And on the other side, we hope hopefully we get benefits because in epistemic logic, we don't know of much work that exposes the underlying topology of Kripke models. And specifically, dynamic epistemic logic, the type of examples that they have been doing seem to be different. And we bring new ideas also to distribute to the dynamic epistemic logic that I will explain. So the setting in general is similar to what Maurice described. We are interested in a system of n+1 processes. And as we can see, there are many choices of how they communicate and so on. We want to fix a very simple setting, both to be able to explain it in the talk and to understand exactly various subtleties about the semantics that completely change. When you really formalize it in terms of logic, they make a big difference. So we assume these n+1 processes are sequential processes, but each one is asynchronous with respect to the others. Every process can run at its own speed independently of the other processes. At most, T of them can suddenly stop their computation by crashing. And communication will be the simplest possible way by writing and reading shared memory registers. And then we are interested in what tasks are solvable in such a system by defining a task, as Maurice described, as an input-output relations on values. And the question becomes then, which tasks are solvable in which distributed computing models? How are, for in this particular case, how are the number of possible failures T? How many processes can crash? How does it affect either the task that can be solvable or how fast that task can be solvable? And here for this work, actually, it's sufficient to consider a very simple version of task where you have a set of input vectors, I, a set of output vectors, O, and an input-output relation. So the set of inputs really you can model them as vectors. An input vector specifies for each position what is the input value of the process. Xi is the input value in the vector x for process I. Similar for O, they are output vectors, and x, the ith component of the vector, is the output of a process I. And then for each I, processes should be able to decide a vector O that is legal for the task specification. That means that the vector O belongs to the relation to delta of I. So the examples, the main examples that actually capture the most essential features in distributed computability are first consensus, the consensus tasks, where the input vectors are just combinations of values from some set of possible input values. And then processes starts with a vector which represents their input values. They communicate with each other as much as they want, and they should decide on one value, which is one of the values appearing in the input vector. The other task, also Maurice mentioned, is central to this area, is k-set agreement, where the processes should decide on at most k different values that were proposed by the processes by their input vector. And the other central task in this area is approximate agreement, where you are required the processes to talk to each other and agree the values that they decide should be very close to each other by a distance at most delta, or in this case 1 over delta. So there are many other tasks, but actually these three tasks captures many of the essential features of distributed computability. And the first interesting observation is that distributed computability is very different from sequential from computability. The modern computer science was born with the discovery by Turing that there is one model of computation, and if a function is computable, it's computable by a Turing machine, and if and only if. So this is the situation that is radically different in distributed computability. First of all, even if each one of the processes of the machine can compute even non-Turing computable functions, nothing changes. It's not about the local resources that makes what a task solvable or not solvable, but it's about the communication, how reliable the communication is, how much failures, the communication, whether it's in message passing, on shared memory. So for each one of these possible variables, you fix the model of computation and the tasks. So a task is just the distributed equivalent of a function. So the first thing we learn is that there is no universal computing model for task computability, because each model, when you change features, the task that can be computed in that model changes with respect to other models. Consensus, for example, is in some sense this area of task computability was born about 20 years ago with the impossibility of solving consensus in an asynchronous system. Even if only one process can crash, already it's impossible to solve consensus. Then this family of tasks was discovered where the degree of agreement depends on how many processes can crash in the system. So k-set agreement, the processes can agree on at most k different values, if and only if the number of crash failures is t less than k. And then delta approximate agreement, which says that actually processes can agree to values as close to each other as they want, even if every process can crash. So this is a very quick, small summary of this area that we collect in our book, which has been active since the 80s. And then, of course, there is also a lot of work in epistemic logic in multi-agent systems. A lot of the work is surveyed in the book by Fagin, Halpern, Moses, and Vardy, Reasoning About Knowledge. But as far as we know, there has not been a study of distributed computability from the dynamic epistemic logic perspective, and in particular connecting the topological properties that we know affect distributed task computability with logical epistemic properties, which is exactly what we do. Okay, so this was the little overview of distributed computability. Now I will give a little overview of the logic notions that we use. So epistemic logic is the basic thing. Epistemic logic for multi-agent systems is defined in terms of a Kripke frame, which is just a graph. The vertices of the graph are S, which are the states or worlds. Sometimes they are called the possible states in which this system could be. And you have an indistinguishability symmetric relation, delta, which labels the edges of the graph. So each vertex of the graph is one possible state of the system, of the distributed system. And you label an edge with a process I if this process I cannot distinguish, cannot tell apart the two vertices that represent two possible worlds. This is what is a Kripke frame. And then a Kripke model just adds, decorates the states of the world. Every vertex of this graph is decorated with the atomic propositions that define what is true, which are the facts that are true. So this is a Kripke model and a Kripke frame. If you have questions, please feel free to, because there are things from different areas and different backgrounds. And then epistemic logic is very nice, because then you can talk about what a process I knows in a given state of the graph, in a given world, in a precise way by the following notion. You say that a process I knows some formula phi in the model M. So this is the representation. In model M, in a given vertex S of the graph, the process I knows the formula phi if and only if the process in every world, in every vertex that is indistinguishable to the process I, the formula phi is true. So this is in some sense how we define knowledge in real life also. When do you know something? When something is true in all possible worlds that you consider that are indistinguishable to you in the current situation. Okay. So, for example, then you can model the possible inputs for binary consensus. In binary consensus, processes start with input 0 or input 1, and this is the whole initial model. What is the initial model? I. So we have an initial model I. The states of this model I is G0, is the possible initial states of the system. Then you label with an edge. You label an edge of these two initial states of the system with I. If I cannot tell apart what are the inputs, his input, the process I has a certain input, but you label all the worlds around it that are indistinguishable to the process I. For example, this would be a little Kripke model for binary input. So you have in this situation 3 states where in alpha both states start with 0. In gamma both processes start with 1. And in beta, the first process starts with 1 and the second with 0. And then you can talk precisely about that a process knows its input. What does it mean that a process knows its input? It means that its input value, say 0, is true in the current state, and also in all the states on which it cannot distinguish around the current state. Yeah, okay. So in this way, you have a model, an initial model for the system, which represents all possible initial situations of the distributed computing system. So for example, for all possible states, initial states where process start with binary input values, you have all these possibility vectors. Each state is represented by a vector, but actually you put atomic propositions that represent the value of process 0 is 0, the value of process 1 is 1, and the value of the other process, and then you put edges labeling hood. So for example, in this, the edge from 0, 0, 0 to 0, 0, 1 is labeled with P and Q because neither P nor Q cannot distinguish between the two states. In both of them, P and Q have the same input values, and only R can distinguish because R has a different input value. So the initial Kripke model would look like a graph like this, but decorated with atomic propositions, which model the input values to the process. This is epistemic logic. So epistemic logic model represents the knowledge of all possible states in a given situation. Here, maybe the initial situation. And now the dynamic epistemic. Yeah.
Sorry, on that previous figure, there's more edges that you just didn't draw. Is that
Yeah, in parentheses, I said not all edges are depicted. Yeah, okay. Yeah. Okay. And of course, I mean, to really be the model, the labels here are really not important. What is important is the atomic propositions which are coloring each one of these states. And these atomic propositions are what are representing really the truth values of the state of the world. What is dynamic epistemic logic? Dynamic epistemic logic wants to understand how a model, a Kripke model, changes when communication happens into a new Kripke model. So the kind of things that you want to do in dynamic epistemic logic is new formulas of the form A square brackets F are used to express the statement that a formula F is true after the occurrence of some communication action A happens. How do you determine whether a formula is true after communication happens in a model M? Then you transform the current model, Kripke model M, according to the possible actions A, that communication A that can happen, into a new model M prime. And this new Kripke model, then you ask in the new Kripke model whether the formula F is true or not. So each action in this, what is nice is that this setting can model complicated actions that can be thought of as public announcements, but that are not completely heard by these public announcements are not heard by all the processes. Some process could distinguish the announcements, and some other process could not distinguish it. And by this, you really can model complex scenarios. Actually, all of these distributed computing systems, as we will see. So the crucial notion in dynamic epistemic logic is the notion of an action model. An action model is like a bit like a Kripke model. It has a set of states A, but these states A are really actions, communications actions that can happen. You have again the indistinguishability relation tilde, which tells you which processes cannot distinguish between a communication event that happens. And then instead of labeling these states with atomic propositions, now what you have is a precondition functions. And what is nice is that this precondition function tells you each action communication to which initial state you can apply it. And then the whole setting of the dynamic epistemic logic is built on, you have an initial model, you have an action model, and then you have the notion of a product update, where you make the product between the initial model and the action model, and you get the new model, the new Kripke model that you are interested. So the product update describes the new model, which is called MA, obtained from the initial model M after the possible actions are applied. And then, these preconditions define states on which the actions can be applied until it represents which process cannot distinguish between a certain action. So more precisely, how do you do this product update from between a model, initial model M and an action model A? The product update is similar to the product of the two states. So the product update will be a model, of course, with the states S prime, with an indistinguishability relation for all the agents, all the processes in the system. And you have atomic propositions labeling, it's just a Kripke model. Each world of S prime is a pair, of course, a pair where S is an initial state and T is an action, and such that the precondition of T is holding S. So if the action model tells you that it is legal to apply the action T on initial state S, then you put a pair ST in the new Kripke model. How do you define the indistinguishability relation of this pair? So a pair of states in the new model are indistinguishable to an agent A whenever it holds that they were indistinguishable in the initial two states, S and S prime, and also and the actions are also indistinguishable to T. And now we need to define how do you evaluate the atomic propositions in the new model. You just copy. Simply, this is a very interesting thing, is you simply copy the atomic propositions from the initial state, S, into the pair. And that's it. This is essentially the core of dynamic epistemic logic, but of course there are many more things. There is a nice book and an entry in the logic, in the Encyclopedia of Logic and so on, but this is the crucial ideas: an initial model, an action model, and the product update. Okay. So what we want to do in the first sort of contribution of this work is show that you can, that with a setting of distributed computability, you can really transform it into a setting like this. You have an input model, which also represents the input, and we want to derive what is the action model for various distributed computing systems. In particular, what we will do is we'll describe the action model A, describing what is the knowledge gained by the processes running some protocol, some communication protocol D in a given specific distributed computing model after each process executes some number of steps of each process. Then you produce the product update according to dynamic epistemic logic, and you get a new model, a Kripke model, which represents the knowledge of what is the knowledge that processes gain by communicating with each other in this specific model of computation. Then the novel thing that we do, that we haven't seen people doing that in dynamic epistemic logic, is that you can also represent the task itself as a product update, as a set of actions. And then the notion of a task in terms of logic becomes a product update. So you start with an input model, I, you apply the action model of the task, and you get a new model O, and this Kripke model is the target knowledge that the processes should be able to gain if they are able to solve the task by the protocol. And then you have a diagram like this, and you have the notion that we have been using in distributed computability of when a task is solvable is translated into a problem of logic by this diagram. You start with an input Kripke model representing the possible inputs to the processes. Then you have a product update of the task, D, representing what is the desired knowledge for a given task. And then you have a diagonal up of a process, what is the knowledge gained by a protocol D in a given model after some number of steps. And now the main notion is that the task is solvable in n steps in the given model of computation if and only if there is a morphism of Kripke models from P to O that makes the diagram commute. So, and a morphism of Kripke models is really just a morphism from the Kripke frame of the protocol model to the Kripke frame that preserves the indistinguishability relations. If two states are indistinguishable to a process I on top, they should be indistinguishable to a process J, and the atomic propositions that are true up in P should be true. So this is a rephrasing of what we have been doing in the book and in all these years in distributed computability in terms of epistemic, dynamic epistemic logic. Now, the thing is to show really that all the models that we have been working on, you can really define an action model that represents semantically the distributed computing set. Any questions? Well, notice something interesting. This notion of dynamic epistemic logic seems at the beginning very strange because the only atomic propositions are the atomic propositions of I. So you have every state here is labeled with atomic propositions, simply describing what are the input values of the processes. You do the product update to P, and then P is labeled only with atomic propositions which talk about the inputs to the processes. O is the target model. Also, by the product update on dynamic epistemic logic, every state in O is also labeled only with atomic propositions about what are the inputs. So the question about delta really transfers into this little nice theorem, which says, actually, if you consider the Kripke model on top and the Kripke model on the bottom, then if there exists a morphism from M to M prime, then agent on top of if the task is solvable, the knowledge in the protocol has to be at least as large as the knowledge in the output target. And formally, this is what it means is that for every agent I, for all states of the protocol model M, if in the bottom target some formula phi is known to A in some output state, then at least this formula should be known also on top in the protocol complex frame. So, so this translates into any form of knowledge that you would want. For example, common knowledge. In common knowledge, which is important in distributed computing. So common knowledge just means that a formula phi is known by a set of processes in some state, and it's also known that they know this formula, and they also know that they know this formula, and so on. And this is common knowledge. So formally, a formula phi is common knowledge to a set of processes B in some model M, in some model, have some model M and some state C. The formula phi is true. It's common knowledge in that state if and only if the formula phi is true in every reachable state from the state S by going along transitions labeled by processes I. So that means that common knowledge, if the output complex is demanding common knowledge, then the protocol should be able to achieve common knowledge in order to solve the task. So for example, a simple way of proving that consensus is not solvable for two processes in the binary case is by you look at the input model, which is composed of these four states where they all start with 0. They both start with 0, they both start with 1, or one starts with 0 and the on. Then you look at the output model, which is targeting either both the side 0 or both the side 1, and you define the output model, and you see that it's disconnected. It consists of one connected component where they know they have common knowledge of what are their inputs, and another connected component where they have common knowledge of what are their inputs. And then if the protocol in a given model is connected on top, then there will not be the Kripke morphism H from O. And then if binary consensus were solvable, we would have a morphism delta from the protocol complex to O, respecting the delta mapping, implying that any knowledge available in O would be available in P, in particular common knowledge. And if the protocol complex is connected, it's easy to see that there is never common knowledge about their input values. So this is just a little example of how you translate a problem of computability, and in terms, really this is the topological notion of connectivity in terms of the existence of common knowledge in a particular logic. Okay, so in terms of the contributions, so what we do is first describe a generic model in terms of traces of how the process is, all the possible executions of the processes in a given model. In particular, we study in detail the asynchronous model with the process can crash. And then roughly we have to define this action model. We see that for the protocols that we are interested, that define computability, that these are these full information protocols, that they don't forget anything, the processes. Then the action model A is defined in terms of the possible schedules of the environment. And indeed, for any number of steps n, the protocol model is connected because it's easy to prove, but it's also well known from distributed computing. And then common knowledge is impossible, and then you cannot solve consensus. So, I mean, in a little bit more detail, how do we define exactly the action model? Then it's something that you have to do carefully because, in some sense, all of the semantics of a given distributed computing model. You can have many distributed, even in shared memory, you can have distributed computing which have read-write variables or even other communication objects like test and set and other objects. So all the semantics of the asynchrony, the number of processes that can crash and so on, you capture all the semantics in terms of the action model, which is just a set of actions. Each set of action is just a scheduler in which is simply really a permutation in which the scheduler can tell the processes which one takes the steps after the other of the given protocol. And then all of the semantics is captured by the indistinguishability relation, telling which processes cannot distinguish between this scheduler and which are the possible schedules. For example, if at most T processes can crash, then in all the set of schedulers would include only schedules where at most T processes are prevented from making progress in every execution. And then we need a little bit of tricks that I prefer not to go into detail of how to actually make sure that that to define the precondition for each action model that applies to which input state it's applied, and how to define the indistinguishability. But everything, I mean, there is nothing complicated. I prefer better to explain you how to define the action model for a task, which is very simple to understand. The action model, how do you define an action model for a given task T? So now what are the actions? Because now there is really no computation, it's really just modeling desired knowledge. So now the set of action points S is identified with the output vectors of the task. So an action point, AC, is a vector which says which is the value that each process should decide in an execution, and is interpreted. The action that could happen is not now a communication action, but is really a conceptual action that says agent A, I decides value DI in this vector, and this is the action. So the action is the process decides in the future, and then distinguishability relation just says which process I does not distinguish between two output vectors if it has the same value. And then this is the product output model for the task. Is simply you take the input model and you do the product with this one. So in the output model, state of the output model for the task will be a pair, which simply says which is the input vector in this situation, which is the output vector T, such that T is a legal output vector for the initial state. Okay. So this is, I mean, the whole setting and that we develop and then that we describe for various models of computation. The last part of this work is actually exposing the topological information hidden in a Kripke model. So a Kripke model seems to be a just one-dimensional structure, but actually if you move to the dual of this, then you get a simplicial complex. And then you can really expose that there is well, what we do in the paper is really prove just precisely that a Kripke model as a graph and the dual in terms of a Kripke is a kind of epistemic simplicial complex where you have, instead of for each simplex you have a facet of a complex. The atomic propositions decorating the graph now are transferred as atomic propositions decorating the complex, and now you can have a epistemic model for multi-agent systems, epistemic logic. And then the action model preserves topological invariance of the initial model. That is why the whole approach makes sense, because when you transfer from the graph to its dual, which is a simplicial complex, then in distributed computing, really there are topological invariance preserves that you can see only in the dual, in the protocol complex. And as we know, how much of this topology is preserved depends on what is the computational power on the model, the reliability, and so on. And then what is happening is that we are really exposing that topological invariance in this simplicial complex are encoding the degrees to which knowledge is not evolving are presenting either limitation to certain formulas being known or actually making possible certain logical formulas to be known. So as a simple little example, if you start with the input Kripke model of the binary inputs where it's hard to see what is the topology, when you move to the dual, you just get a kind of sphere where each triangle corresponds to an initial state of the system, and a process belongs to the intersections of two facets if the process cannot distinguish between the dual of the two graphs. Okay, so this is all I wanted to say today. We have provided formal semantics to distributed task computability using dynamic epistemic logic. Then we have various examples of how questions about task computability become questions about the possibility of knowing logical formulas. So it's not so much interesting. In summary, what we are exposing that is not very important what is the values decided by the processes. The whole thing that the only thing that is really important is this iterated knowledge. Processes know, and so on. And the structure of this nesting of knowledge operators is encoding really the whole demands of the task computability, and not really what exactly output values the processes produce or not, because they don't appear at all, the output values, just the logical formulas about the inputs, about knowledge about the inputs, Then we use the dual to expose knowledge. And this is a work in progress. We are working in several directions, and there are many open problems. For example, one interesting thing is that it's not so clear when we work in our context of distributed computability. Sometimes we consider tasks that start in only one initial input state. So in this context, you see if that there is the initial Kripke model has only one initial state, that everybody knows everything about the inputs, and there is nothing to compute. They already know what their inputs are, so they can produce outputs without any communication at all. So to define this kind of inputless task, we have considered you have to actually incorporate more knowledge about the model, not only about the task, but also on the specific thing. In the action model becomes more complicated. We develop that also. Another interesting thing is that these action models compose. In dynamic epistemic logic, one of the first things they prove is that you take an action model, you take another action model, they compose them, and you get another action model. So this should be very nice to discuss distributed task computability, because many of our models have this structure of round structures that you can compose and obtain. So we have not explored this very much. And of course, study other distributed computability models. For example, how do you formally give a formal semantics to the Byzantine models that Maurice was discussing, where processes can lie? Then you have to explicitly say what are the possible words of the lies that are possible, and so on, and give a formal semantics. Synchronous models are interesting because processes can crash, and once a process crash is detected by everybody, and then the dimension of the simplexes goes down. And then you need a little bit more in the Kripke model, you need more additional details to model these lower dimensional simplexes. And an interesting problem on which we are working is, if a task is not solvable, in terms of topology, there is some topological obstruction. How does this topological obstruction is translated into a logical formula, which says this logical formula is exactly what cannot be known? Another interesting question is how to define subdivisions, the subdivision operators, in terms of a logical formula about knowledge, and so on, and many other interesting open questions.
model for distributed computing?
Yeah, no, not yet, because it's not clear, because one thing we do in distributed computing, which simplifies a lot for task computability, is we want to understand which tasks are computable and which tasks are not. So for that, it's sufficient to consider these canonical protocols of communication that are full information. It means that you say everything you know. Each time you send a message, you say everything you know. You never forget anything. In logic, in general, they are very interesting in many subtle scenarios. Suppose I say this, and I forget this, and I believe this. So, to analyze arbitrary distributed protocols where you can say forget things and say only part of what you know and so on, it's not clear that always you can define an action of what would be the action model or so on. Probably yes, but it requires to tune the action model to the specific protocol and so on to give a very precise semantics of what is happening. So it's not completely clear that. I assume my conjecture is yes, but I don't know how complicated the models get and so on.
I was going to ask, what about long-lived computations?
Yeah, that's another whole research area. This is the simplest case where process starts with inputs, talk to each other, and produce outputs. And that's in distributed computing. Often we want continuous computation, where I don't know, in a web server or something, continuously there are inputs, are computation, continuously outputs. So how is knowledge moving and evolving is also an interesting question. Difficult because also in our setting we understanding less well than the task, but this of course would be a very interesting direction also.
Thank you, Sergio.
Okay.